But we're on episode 36. It's a beautiful day to learn about ultrasonics and piezoelectric devices. And I have something that people might be interested in learning about is what is the cheapest way to measure the impedance response of an ultrasonic transducer. Before that begs what is impedance again. I'm not going to go into detail about why you want to measure and what is it. Hopefully you do know, but if not, search my YouTube channel, search online, find out why you might want to measure that impedance response of your ultrasonic transducer. But if the equipment basically that's typically used to measure this in research and companies is an impedance analyzer. And that equipment is going, the standard kind is going to run you like $30,000 new. If you're running any type of serious operation, you're going to want something recent and calibrated. If you're going to have to go to the pains of calibrating such devices and keeping that record, you're going to want to get the good stuff. That being said, there are good alternatives, and those alternatives are either cheaper, more capable in different ways, more flexible. So there are options for you for sure. And I'll explain why you would want a commercial impedance analyzer, the 30K kind from Keysight or Agilent, or in what cases would you want to opt for something else, for a different brand, perhaps of impedance analyzer. Let's get started. My friends, let's answer this question that what is impedance? It's the response, and there's an actual subtle point here. It's quite important. It's the voltage drive and the current draw. So you have that ratio, you end up with a unit of ohms, but it's at a frequency. So there's an impedance at 1 kilohertz and 10. This is why when you drive your device with a square wave, you will not be able to measure impedance, at least very directly. You can measure it indirectly using frequency, fast Fourier transform stuff, but that gets a little bit hairy. Just use a sine wave. Generate your stuff like that. It's going to be a lot more accurate as well. You won't have to be filtering out, and you might lose some info in that process. So it's the response of your device, and obviously the electrical response is related to the mechanical response, and therefore using electrical measurements, you'll get electromechanical information, which is great for understanding your quality of your device, tracking its performance, understanding and troubleshooting it, creating tolerances. It's a wonderful thing to have. So what are the measurement methods that are used? One thing that came to mind that one of my regular viewers, wrote to me and asked, can I use such and such LCR meter to do this impedance analysis? I really don't want to get a commercial impedance analyzer that I keep reading about in papers. Would this one work? Yes and no. So LCR meters, there are two types. One is fixed frequency. So the LCR meter will measure at 60 hertz, 100 hertz, 120 hertz, 1 kilohertz, 10 kilohertz, maybe 100, but usually you'll stop at 10 kilohertz. That's used for analysis of passive components that have a relatively stable trajectory. That, for example, for a capacitor, as you increase frequency, the impedance drops, but capacitance stays the same. And there's a similar opposite story for inductance and resistance as well. So you don't use an LCR meter to analyze resonators because they can only operate at specific frequencies. So you won't be able to get to your resonance, and you don't have. So what you can use, if you do choose so, and these are cheaper than impedance analyzers, there are LCR meters with continuous frequency sweep. That will work 100%. However, they sometimes lack a nice display. So you'll have to extract the data to your computer, which just adds an extra step, which can be annoying actually. So I would just let you know there, if you can program something up, click a button and kind of have everything work out for you in terms of your analysis, then please do so. That's a fine method, and you'll end up being cheaper, and you'll get a calibratable device, which is very important for researchers. We kind of researchers skimp away from getting calibrated stuff, but it is, even if you're not calibrating your equipment, you have to make sure that it's working correctly, that even whether you calibrate it or not. So let's get on to the next part, because probably a lot of the error in electrical equipment is not from calibration. It's from user misuse or stray cabling, for example. That leads to issues. Now, if you get to the bare bones type of thing, like what are you exactly doing when you measure impedance? You're measuring voltage, you're measuring current in a way, and you're measuring phase. Well, guess what? 3 instruments can provide all that for you. You can use an oscilloscope to measure voltage and current, assuming you have some type of current measurement. Either it's a ground side resistor or it's a current probe. You have a function generator to generate the signal. These components are sufficient to measure impedance. The only issue here is the manual annoying nature of kind of having to turn a knob or change frequencies manually and get that all done for you. But that's something you can program. I also have a video series on in which I describe the programming of such a frequency step system, where you step up your function generator to the next frequency and then you record your voltage and current and you kind of keep stepping through that process. Yes, you can actually generate an impedance curve without having an impedance analyzer, because what it's actually measuring is defined as voltage drive divided by current draw at a frequency with a phase. If you get all those, you got it. But the issue is that how accurately can you do it with an oscilloscope? There's a lot of post-processing that might need to be done, especially in order to resolve phase very accurately. There are methods of doing it, and there are challenges in it. But I've done it. You can do it too. So the next part is a network analyzer. So the network analyzer it is less accurate than an impedance analyzer in some aspects. In terms of measuring high impedance values, it's mainly used for RF, high frequency, which tends to be low impedance. So they have different specification ranges than impedance analyzers. Although some devices may double, some don't. So you should look at your specs. Like for piezos, you're not going to need something that goes to a gigahertz. You're really not. I would say 10 megahertz is the maximum, but you'll find on impedance analyzers, the expensive kind, they go to 120 megahertz. Well, bulk ultrasonics, well, why? You need 10 just if you want to measure thickness resonances. That's kind of why. Of your transducers or of your ceramics. So network analyzers, they're kind of used for a different application, but they can go with measurement of ultrasonics. I don't have a lot of experience in using network analyzers like electrical, for transmission and those sort of S parameter analysis, but that's what I have to mention for network analyzers. Look at the specs and see if the one that you have is going to work for you, because their output and their interfaces are very similar in some cases to impedance analyzers. So impedance analyzer, I guess the holy grail, the Agilent or the HP, which became Agilent, which became Keysight, that is the standard. If your company can afford such products, they should purchase them if they're going to be working in the area for a long time. They're very accurate. Quite frankly, they're the standard of measurement. They're calibratable as you'd expect, and they have a lot of functionality in order to get you accurate measurements. So it is a valuable test instrument for measurement of impedance. But the question was asking for the cheapest one. So now we're going to get to one decent cheap option. It's the Digilent Analog Discovery. This is basically like a USB oscilloscope which has multifunctionality to it. One of the multifunctionalities that they wrote a program for you, and you can buy an impedance analysis kind of plugin which measures current, helps you measure current through ground side resistors and relays for switching. So it's kind of very plug and play for you. This is going to be like $400 for something new. I would recommend that someone who's developing, not ready to invest in an impedance analyzer, wants an entryway to understanding what they really need and want, that they go with this option. I haven't used it myself, I'll be honest, but I have seen some clients and some people I've spoken with just for kind of that were able to use this. The frequency that it can go to is quite high, so that's nice. I think it goes to 10 megahertz perhaps even. So that's actually pretty good for impedance analysis. All right, so let's go to the next one, which is the Chinese impedance analyzer. This is one that you can buy on eBay. I think that's the easiest place to get it. You type in impedance analyzer piezo, you'll come up with all these options. I have seen that they have worked for people. I don't know about the calibration. There are even some made for piezos, and I'm sure they're used internally in piezo factories, and therefore they decided to start selling them on eBay and whatnot. I don't know what the reputation, the international reputation of the companies creating them, but many times I've seen two of my one company that I've worked with off and on, and one that I regularly work with have used this, not seriously in production use, but it is useful for learning and understanding. I think it'd be quite a capable device for that for sure. So there's what I have to say on that. The next is what's called the TRZ analyzer. This is a company that develops different acoustic measurement products, some of them specifically around piezoelectric transducer measurement. So this is the device. I believe it goes into maybe 1 megahertz or 100 kilohertz. It's a low voltage measurement. The claims for the device, the technical specifications, so it to be more than good for all kind of power electronic piezoceramic measurements and transducers, but it doesn't go to higher power levels, so you won't be able to monitor that. But things like resonant frequency, resonant impedance, at least at a specified voltage, which can be used for technical specifications, that is all good there. One of their big marketing areas is ultrasonic welders, assembling them, noting the frequency changes, doing a little bit of diagnostics. That's some of the use case applications, but they have a very capable program. I haven't used the device personally myself, but there's a very capable program that comes along with it. And I look in. It's a few $1,000s, but it's something specific for piezo, so it's tested in that fashion. So that's the part I really like about it. It's a bench unit, and it's very simple interface, and it has the mechanical interfaces is good, and the main interface is actually on the computer. So you're kind of forced, thankfully, to save directly on your computer. And remember, any of these devices, including the oscilloscope, any of these devices, including the digital and analog discovery, I believe that whenever you can use your computer to collect data, then you can do screenshots, which are really nice to do. If you whether you use USB oscilloscopes for whatever reason, and any other type of a device that you are remotely connecting to and receiving data from, and perhaps it has a native computer program app that comes with it, that comes with your device, screenshots are so nice to have. All right, there's the last two, the notable mentions. So the one is Piezo Drive. So Piezo Drive is a company that develops ultrasonic amplifiers for ultrasonic devices. They also have a box which has an amplifier built in. It has so you can do high voltage frequency sweeps. You can do like constant current frequency sweeps. It also has the additional functionality of locking onto a certain phase. So that's also a very capable solution for that. Higher voltage, it's in the range of several thousand. It's not extremely expensive, much less. I believe it's going to be much less than your impedance analyzer for sure. It provides a lot more functionality, but it's not exactly a standard measurement device, which makes it, I don't know if it's suitable for calibration, and this is an I don't know question. I don't know thing. I don't know if it's suitable for calibration and quality assurance, but definitely for development, it's been really successful. I've seen companies being successful with it. The final and mention is a closed loop transducer analyzer. That's a product I offer through my company, and in that product, the current, power, or voltage is controlled over the frequency sweep. The system uses a ground side resistor for current measurement. A USB oscilloscope is used to gather all of the data, and there's also a user interface that comes along with that on the computer. There's kind of some consulting involved in it, so it's a kind of a full package deal on getting that implemented into your system. The USB oscilloscope is also calibratable. I also have another product which is called the Ultrasonic Heartbeat, which does almost like a data acquisition style system, so that same oscilloscope can also be used for that aspect too. So let me know if you're interested in that. But I think I gave a long, detailed explanation. What I'd recommend for that person to purchase would either, who asked the question, would either be to purchase an LCR meter that has constant frequency sweep, to build your own. It's not hard, but you got to spend a little time on it, and it's going to be limited in its functionality. But guess what? All devices are limited. They are. You have to drive with your eyes open. Even if you're driving a Tesla, you got to drive with your eyes open. Sorry about that. Autonomous driving is far away, so is autonomous measuring. Like, throw anything in there and just measure it. No, that's not good. So some of those issues can be solved with good follow-up. But another device that you could look into is the LCR meter with continuous frequency sweep. The digital discovery is pretty nice too, because it comes with a computer user interface, and it's cheap. So you have been watching the Piezo SHOCK Show, episode number 36, with your host, Dr. Shakani, answering your questions on ultrasonics. Go to the links and find the presentation notes, find links to sign up for my email list, and you'll get updates for these videos every day, including those slides in your email. Also, check out my services and offering if you're if you're interested in hiring me to help give a boost to your ultrasonic transducer development project. Thank you, and I will see you tomorrow.